our last speaker, Rene van Zuuk from Netherlands, an amazing architect, and his presentation about technology that defines architecture.
My name is Rene van Zuuk. I've been an architect for 25 years, and next to that I have been a teacher for 17 years. And all the work we do is related to building production technology. If you look at the building industry, you see that the building industry always starts with a raw material, a material actually which enables you to make anything you want. But that's not what the building industry does. As soon as the building industry gets their hands on a product, they make little modules, rectangular blocks, profiles, bars, and plates. And if you use those elements to make your components, make a foundation, it's bound to get a rectangular foundation. And you're going to make a rectangular structure. And in the end, you end up with a rectangular building. About 25, 30 years ago, computer software, design software was introduced in the architectural office. And in the beginning, the computer software was a very elaborated drafting machine, which enables you to draw a drawing, change it, and have the same new drawing afterwards. But it didn't take long before computer software could make 3D drawings. And nowadays, the computers can almost design anything you want. There's no limit anymore. The only limit is the building industry. They just can't build it. Only a few architects in the world can do that, because they more or less have unlimited budgets. I'm a Dutch architect, so I have to work with a budget which the Dutch clients allow, which means we have to work with the building industry, and we have to find out how can we model our project such a way that we can build it for a reasonable price. This is a photograph of the Architectural Institute, and we had total freedom. The only thing was, the limit was the budget. And we made it a shape, but what we did, we just folded one plate, and that meant that we had a singly curved surface. And by making the singly curved surface, we knew we could make a structure from straight beams and perfect curves. And that means any steel company in Holland could build it. 3 years before, we got a commission for a pavilion in Zeewolde. And Zeewolde is a town in a rural area. And they were all farmhouses. And every farmhouse got a barn from the government. And that barn had a 3-hinge structure. That means that you have 2 hinges at the bottom and 1 at the top. And what we did, we just shifted the hinge. That meant we could make a structure which we could twist. We could rotate the trusses, and therefore we could make a warped building. But the nice thing about twisting a project like this is that if you clad it with folded metal, you don't have any waste of material. You can just, one of the qualities of the folded metal is that you can twist it. So everything your client buys is actually on the project. This is the final project. And you see the warped roof. 3 years after the Architectural Institute, we got a commission for a pavilion in Roosendaal, right in the center of town. Our client wanted to have an egg-formed pavilion. Also, the urban designer wanted that. To make an egg-formed pavilion, you have to be really careful that you don't make a very complex structure. So what we did, we just put a 3-dimensional grid, rectangular grid on top of it. So at least 80% of your floor plan will be straight, and you only have, I don't know if that worked, only have the sides which are curved. And then we started playing with the structure. We lifted it up, and we got a roof where you could actually walk up on top of the roof and make a square on top of the garden, or the top of the square of the city. To work with the building production technology, you have to know how the system works. In 2003, we got a commission for our first apartment block. We never built apartment blocks before. So we did some research. And we found out the cheapest way to build apartments in Holland is to use a concrete structure and to use a tunneling system. And a tunneling system is a system where you have two ends, and you put them next to each other, and then you can cast the floor and the wall in one session. And that goes very fast, and therefore is very cheap. If you look at the qualities of that tunneling system, then it's very rigid in the width and the height. You can't change that. But you can very easily change the length. So what we did, we made a structure where you have a fluent front and a fluent back side of the building. To be honest, this was only 4% more expensive than a rectangular one. But to be honest, it's never the structure which is the problem. It's always the skin. The structure is more or less two-dimensional. The skin is always three-dimensional. You have to stretch the skin to close the wall. So we looked for another system. And that system, what we found, was pod ceiling. Pod ceiling, you put panels on top of each other, and because you put them on top of each other, there's an overlap, and you could change the overlap. So therefore, you can change the length of your panels. And we use that system to cover our building. And we got panels which are all equal. At the moment, we just finished another apartment block, and this was in Hilversum. When we start a project, we always do research on the site. We walk to the site, see what's going on, or get a feeling of the site, and then go back to the office, make a 3D model of the surroundings, and start playing with models to what could be on that site. So we made a block like this, a plaster block, and just from this we knew we had to make an all-sided building. Then we go back to the data. What does the client want? And in this case, he wanted to have 55 apartments to make the project feasible. And then we took the information of the city. And in this case, we found out that all the main infrastructure of the city was going right through our plot. And we were left with a very small surface where we can build on. And that meant that we can only have 4 apartments. We were allowed to make 11 stories high, and that meant we can only make 44 apartments, not 55. So when I saw that, I went to my client and said, okay, we can only make a building which looks like that, because otherwise it doesn't fit. And the client agreed, and our first design we made was actually a design like a hurricane came. The balconies were stretching out, and everyone was really pleased. The only problem, this project started in 2004. In 2008, all the working drawings were finished, and then the crisis came. And we had to cut the budget again. And that meant we had to make a new design. And the new design we made, we'd use the tunneling system again. And we can't leave it the tunneling system. We made a cross in the middle, and we extended it to the outside. In the end, this was the render the client made, or an office from the client made. And the building is just finished. This is the final building. In 2006, I was a professor at the Technical University in Eindhoven, and I entered a symposium like this. And I told my audience what would happen if we could print houses in the future. If we could print buildings, that would change architecture dramatically. At that time, everyone was thinking that was 2006, so actually the whole audience was laughing, and they had something that's not going to happen in 100 years. But only 2 years later, Enrico Dini, an Italian entrepreneur, had a printer which could print 3 by 3 by 3 meters. 2 years later, he had a printer which could print 6 by 6 meters. And that's already the size of a house. Dini's system was a system of layering. You put a layering of dirt down, you put a raisin on top of it, and you put another layer of dirt down. And that's how he builds it up. The advantage of that system is you can make anything you want. The disadvantage is that it is very slow. Now, 10, 15 years later, a lot of universities, also our university, has a 3D concrete printer. And they start experimenting. So it's going very fast. And those systems are more extrusion systems. This is a Chinese system. And they claim that they can print a house in just one day. So that's very fast. When I retired as a professor from the Technical University in Eindhoven in 2010, I asked my students to make a sequence. So I told you 3D printer could change architecture dramatically, because it is a whole different way of building. And I said, why don't we make a sequence, and starting with a typical Dutch house, and have the steps what will happen if you 3D print a house. And probably the first thing you're going to print is the structure. And if you print the structure, it is very unlikely that you're going to make a straight line between the walls and the ceiling. If you make a curve, it takes less material and is structurally stronger. So why wouldn't you do that? The second step is if you get more nozzles on a printer, you can probably print the structure, the insulation, and the exterior wall. And that means that the building even becomes more fluent. Sorry, can I go back? No, I did something really wrong. The fourth step is, why would you bring all the materials to the building site? Why can't you just use the dirt which is there, put it in the machine, put glue with it, and just make it from the local materials? And the next stage is just, why doesn't the building become autarkic, so self-sufficient? And the last one was something typically Dutch. 50% of Holland is underwater, which means we pump every day to keep the water out. What happens if we stop pumping and just make floating houses? That was the end result, what we had with students. And we really tried to have a kind of evolution from starting from the start and ending up with the final building. And people often ask me, Rene, do you think that houses are going to look like that in the future? And I have to be honest, it is very unlikely. If you look at all the innovations we have in the building industry, it hardly ever leads to another kind of architecture. So it's very unlikely that the house of the future is going to look like this. Exactly the same as we always had, just from another material in another technique. Like we do now, with the windowsills, the aluminum profiles, and everything is actually transferring to the old and going back to the old system. And that's exactly what the Chinese company does. They printed their houses, and this is what they sell. They don't sell a new kind of architecture. They sell their old architecture built on a new way, with the problems what they had before. Normally, if you look at the set of rules we have within architecture, an architect is more like a collector of techniques and materials. And what he does, he just makes a composition. If it becomes more difficult, more complex, the building, if it becomes curved, the industry is going to punish him with a very expensive building. Once you start printing, that set of rules is changed. A printer doesn't care how difficult the design is. The printer just wants to know, do I have to put a spot of material here, or do I leave it open? And the only three elements which are important for a printer is, how much material do I need, how much does the material cost, and how long does it take to print? Those are the new set of rules if you print. And really, why would you print buildings if they're just rectangular buildings? The current building industry can do that much better than a printer can ever do it. But what if you're asked as a contractor to build this? This is almost impossible to build with the rectangular elements from the building industry. And a building site like this is a contractor's nightmare. I'm going to the EPS, to the polystyrene. After I left the university, I went back to my office. And I was really eager to start making projects which were 3D printed. The only problem I found is that to implement that would take at least 10, maybe 50 years. And we needed to build projects now. So we looked for another technique. We looked for another material. And the material we found was polystyrene, EPS. The nice thing about polystyrene is it's a very cheap material. And you can actually, with a hot wire cutter, you can cut any shape you want. You can clad it with wood, and then it becomes a sandwich panel. You can plaster it, and then it becomes fire protective. You can spray it with hot spray, and you can really make smooth objects of them. And you can spray it with concrete, and then they become structural shells. So the first thing we did is we built a hot wire cutter at our office to make models and to experiment. And the first experiment we did, we made an arch. So we cut an element like this. This is 3D cut, so this is a warped element. And we made this arch. And we were really pleased. We thought, okay, this is a beautiful element. It was translucent. And we thought, this is perfect. The only downfall was when I looked the next morning at the amount of waste we produced. We cut this element out of a block, and we were actually not reducing the arch as a main product, but as a side product, we were cutting almost 80% of waste. And that's what you see in most of those projects. This is the arch, and that's the waste. And if you have a new system, a new technique, it will never be sustainable if you only produce waste. So we started looking for another system. And we started entering competitions. Because that was nice, you have a client, and if you win, you can build it. And the first competition was a track, which was in Holland, around the lake, and all kinds of projects came on that. And we chose the project of a chapel. And what we did, we made shells, and they were with plywood on the side. And all these elements were more or less nested. So we went back from 80%, 5% of waste, to 30, 35% of waste. We won this competition, and hopefully it's going to be built in the next 2 years. But still, we had waste. And we didn't want to have waste. So we looked for another system. And when I looked for that system, I thought, okay, when I was young, I played with a toy which is bucket in bucket. I mean, you probably know the little buckets on the beach. And if you put them on top of each other, you can store them very small, but if you put them on top of each other, they're 7 times the original size. So we looked for another competition, and this was a competition next to a castle, and they asked for a folly. And the design we made was the copper room, and that was a room to exhibit in. And we started with a square ground plate, and we morphed the whole form to the silhouette of the castle at the top. And we did this with software, Rhino and Grasshopper. So we generated it by the computer, those elements. Then we cut a square plate. So we started out with a square piece of EPS foam. We cut under an angle, and we cut in such a way that we could stack all the elements on top of each other. And that meant we could make a pavilion which had a free fall without any waste. We won this competition, and we could build the pavilion. And we used the same data we had on our machine at the office, on a big machine, which was enabled to cut blocks of 5 meters by 2.5 meters high, and in this case 50 centimeters deep. And it took only 1 hour and a half for the machine to cut half the pavilion. So in one day, he could cut the whole pavilion. We cut the pavilion. And you can just take out the blocks and put them on top of each other. And they're light, so you can easily build it out. Put hot spray on the outside. And then finish this with a copper coating. And the copper coating is 80% of pure copper and 20% of polyester resin. And if you sandpaper that afterwards, it just becomes copper. Looks like copper, reacts like copper. It is copper. And the foundation is just a wooden frame. And we put the elements on top of it with students. So having made this system, we then started working on more complex designs. And one of the designs we did afterwards, it was actually competition number 3, was a design for the pavilion in the sky. We thought, okay, pavilion in the sky could be about devils and angels, about the book Revelations out of the Bible, where Archangel Gabriel was fighting back the devils. The second thing we thought about, a graphic design by Escher, a Dutch graphic designer. And what we did, we made the skylights from angels and the columns from devils. And again, we started with a rectangular block. And we cut the rings out of that block. And we erected it, and we ended out of that block we got this pavilion. And you see the devils at the top, or the angels at the top, and the devils are the columns which are in it. And 2 columns we took out to get an internal space. We didn't win this competition. We actually also didn't win the fourth competition, which was a competition in New York about the waste of material. EPS foam is a perfect building material. There's no animal in the world who can eat it, which means it will last for 100 years. And that's good for a building material. EPS is the worst material to make temporary products. You don't want to have a hamburger bucket with EPS, because the EPS gets polluted so much that you can't reuse it. And that means it comes in the environment. In America, about 10% of all the EPS is reused. So that means that 90% ends up on waste belts, and it's going to stay there forever. That means that also 90% comes in the ocean, and that's what you really don't want. So when we started with this project, we started with a square again. And we wanted to have a free form, so we cut it in 4 pieces, and we rotated those pieces. And we cut the angles out of it, and actually we made an iceberg there, out of a square. Put a coating on top of it, and you have a smooth surface. All the forms which are in it enabled to make strong elements, to make the whole thing work, and that you can make an 8, 10, 11 meter high pavilion from that stuff. The nice thing to work with an algorithm is that you also get things for free out of the algorithm. This straight line is not just a straight line, but those are the entrances of the building. If you rotate it, they end up in the outside as being the entrance. Again, we didn't win this competition, but we won the next one again. And this was a competition issued by the Dutch government. And this is about refugees coming from all over Europe, all over the world, to Europe. Most people end up in the neighboring countries. So Lebanon, Turkey, they have millions of refugees. Some of them, most of them, end up in tents. Some of them end up in tents in Brussels. A tent is, in the summer, maybe bearable, but in the winter it's pretty cold. So, in Holland we don't do that. We don't put people in tents. We put them in sport facilities. Warm, dry, but you don't have any privacy. So the Dutch government issued the competition to make a temporary house. Normally they put those people, or put the refugees, let them live in houses like this. But these houses only are built for 2 or 3 years. And after that they're demolished. And that makes a huge amount of pollution. So we gave them a solution. Why don't we make an insulated tent? Why don't we make an insulated pavilion from foam with a surface on top of it? The foam is reusable, the tent is reusable, so you can put it instantly down and you can tear it down instantly and reuse all the material. We designed 2 elements, a corner element and a middle element, and if you put 2 corners together, you got a small house for father and mother and 2 children. If you put 2 corner elements and a middle element together, you get 2 houses for 2 couples. This is only temporary for a few months. And if you put 2 corners with a lot of middle segments, you get single houses in between. The nice thing about the cutting system is that you actually don't, everything is nested, so you don't lose any space. So the government can make boxes, store them, and really if they use them, they can build them in a very short time. This was the interior, and this was the final design we made with a foil outside so it would reflect in the sun and in the cold. If you decide not to reuse them, you can make a temporary house for them. So, and actually those are quite nice houses, so you can put a garden house. Because we won that competition, we made a mock-up, and this was in a Dutch design week, and about 200,000 people came and visited the pavilion and looked what it was, including the Dutch Queen. We started with the foam cutting technique in the crisis. At that time, it was almost impossible for us to build the project we were building before, because they didn't just want to spend the money on it. The crisis is over in Holland. We survived the crisis. We took the material with the EPS because the material is cheap, the technique is fast, and it was available. So you can use it instantly. And we started experimenting. We survived in the crisis because we did a lot of infrastructure work. So we started designing bridges and infrastructure works. And now we're building a bridge of 130 meters long with a very special opening system, which hasn't been done in the world before. And we now just made a bridge of 500 meters with a floor plan which just curves around the water. But we still make project with foam. Just before the summer, we issued a building permit to the city of Hilversum, where the first 3 stories are traditional built, but the roof is made from foam, covered with slices of brick, and hopefully we get a building permit afterwards. Thank you very much.
Dėkojame visiems už kantrybę ir pranešėjams už įdomias temas. Kviečiu visus nepabėgti ir dar kartelį pasivaišinti lavazą kava bei Dzūkijos skanėstais ir nepraleiskite progos pakalbinti mūsų šauniųjų pranešėjų. Ačiū Jums labai.